I am Dr. Gaurav Saxena and I taught Fundamental of Electronics Engineering in first year, and the code is BEC 101. I am Associate Professor in EC department. So I just continue some topics related to the emerging domain in electronics engineer. So this is the topics. So this is the unit 1 topic. So I just cover this is the whole of the syllabus of that particular uh, subjects, and the first unit is dedicated totally the semiconductor diode and what is the application of semiconductor diode. And first one is the what is the VI characteristics, ideal and practical diodes, what is the diode equivalent circuits, and the Zener diode. So I focus on what is the VI characteristics of ideal diode and the practical diodes, and what is the diode equivalent circuits, piecewise linear models, and the approximation models, and the ideal models. So the suggested book is Robert L. Bollestad and the Lewis Neslesky. This is the electronic devices and circuits. So this is a very important book regarding the fundamental of electronics and electronics engineering. What are the syllabus? What is semiconductor diode? So semiconductor, what is the meaning of semiconductor diode? What is the semiconductor whose valency is is 4 and the last orbit electrons is 4? So we can say this is a semiconductors, and we already discussed in the physics ki germanium silicon are very useful semiconductor which has to be used in the semiconductor diode, and this is a single crystal diodes. So we cover the single crystal diode in that particular topic, or we can say indirect band gap diodes, indirect band gap materials. So that means this is the indirect band gap materials and this is the direct band gap materials. So what is the direct band gap materials? Direct band gap material just like a gallium arsenide, cadmium sulfide, gallium nitride, gallium arsenide phosphide. This is a direct band gap material. So that means what is the meaning of direct band gap material? In direct band gap materials, the momentum and momentum are valence band and the conduction band momentum are which are not aligned. So we can say this is a indirect band gap material. So this is a valence band and this is a conduction band. So that means they are not in same momentum. So we can say this is an indirect band gap material. So indirect band gap material are germanium and silicon, or single crystal compound always has a indirect band gap material. But in the direct band gap material where valence band and conduction band are same momentum, so we can say this is a direct band gap material or compound material. So basically we have to be construct a device, electronic device, just like a simple just like a diode, which has to be constructed by germanium, silicon and gallium arsenide. So if we use a gallium arsenide, so that diode is to be converted to the LED. So all the LEDs are to be make, one of the material is gallium arsenide and the simple PN junction diode is to be made by germanium or silicon. So diode is be invented in 1939 and the germanium is to be invented in 1947. The transistor is to be born in the that means the in 1947. So silicon 1954 silicon was used for in 1939 germanium is used, but after that 1954 silicon is used. So in shells we have to be just see that what is the germanium. The germanium atomic weight is 32 and that means 2, 8, 18 and 4. That means the 4 valence electrons in the outermost cell. So we can say this is a semiconductor material, and but in the silicon this is 14. So 284 is the configuration. So in the last orbit the 4 free electrons or valence electrons is to be here. So we can say this is a semiconductor materials, and this is the configuration of silicon. And you see that this electron, this electron, this electron, this electron having a 4 valency, and the energy gap between the valence band and the conduction band is in the range of 1 to 2 electron volt. So we can say this is a semiconductor. In the semiconductor, the energy band gap between the valence band and conduction band which lies in the 1 to 2 electron volt. But in conductor, the energy band gap is confined like 0.01 electron volt. But in the case of insulator, the energy band gap is greater than 4 to 6 electron volt. So, on the basis of energy band gap between the valence band and conduction band, we have to be differentiate semiconductor, conductor and insulator. So, we have to see that the energy band gap Eg for germanium is 0.67 and the energy band gap for silicon is 1.1 electron volt, and the gallium arsenide, the energy band gap is 1.43 electron volt. So, this is the periodic table. And what is majority carriers? Two currents through a diode. What is the meaning of majority carriers and the minority carriers? So, basically germanium or silicon are intrinsic semiconductor. So, what are the extrinsic semiconductor? If we add a impurity, so this semiconductor is to be p type or n type. If we add a pentavalent impurity, so the whole of the structure is to be created by n type, and if we implant a trivalent impurity, so this type of semiconductor is called a p type semiconductor, or acceptor ions we have to be here and the donor ions in the n type materials. So, this is the configuration of PN junction diode. So, if we taking in a silicon or germanium bar and we implant a p type material in this case, and the n type, if we implant n type material in that particular area, so we discover a new devices. So, we can say this new devices is called a PN junction diode. So, this is the internal structure of PN junction diode. Here you have to see that in the p type material, the holes are majority carriers and the electrons are minority carriers. This is the electrons and this is the holes. So, we see that the holes are majority carriers and electrons are minority carriers. This is ions, this is negative ions in the p type and positive ions in the n type. So, and electric field is to be implanted from plus to minus. This is the potential barrier or E internal or E barrier. So, this region is called where no mobile charge is to be here. This region is called the depletion there. So, the PN junction diode is to be work in the forward bias and the reverse bias condition. So, this is the symbol of PN junction diode, and this symbol denotes the diode current, and this one is P and this one is N, and the direction of current in that particular diode from P to N. For diode, when the forward biasing, so we can say if P is to be connected at the plus terminal and N is to be connected to the negative terminal. So, we can say this type of diode works as a forward bias diode, or we can say if we implement in the short and open circuit, if we take this diode as a ideal diode, so this diode works as a short circuit. That means at that short circuit, the resistance of diode should be 0 ohm. But in the reverse bias condition, when P is to be connected to the negative terminal of the voltage and N is to be connected to the positive of voltage, so this in this condition the diode works as a reverse bias condition, or that we can say this is open circuited. That means the open circuit, that means no current flow. So, this is a unidirectional device. So, we can say this is a unidirectional device that support the current from positive side to the negative side of P to N in forward bias condition. In forward bias condition, what is the forward bias condition? In where P type terminal is to be connected to the positive and N type connected to be connected to the negative terminal. So, we can say this diode works as a forward bias. In forward bias, least resistance is to be here, and the reverse bias maximum resistance is to be here, or we can say this is the forward one. This is the reverse. This is the forward one when P is to be connected to the positive terminal of the battery and N is to be connected to the negative of the battery. So, this is the forward bias. In this bias condition, the depletion layer is to be narrow. So, but in the you see that when we connected P type terminal to the negative terminal and N type to be connected to the positive terminal. So, we can say N type, in the N type the majority carriers is electrons. So, they attract from this P plus terminal and no electrons or holes or majority carriers is to be placed between them. So, we see that the depletion layer is white. So, that means least current flow in that particular condition in reverse bias condition. So, this is the I already explained to you, if no external voltage is applied, a very few current is to be flow due to the thermal drift, and the range of that particular current in the range of microampere or nanoampere. Ideally 0, but thermal drift here. So, some of the covalent bond is to be break. Then at room temperature, some of the majority or minority carriers to be flow from P side to N side and N side to P side. So, some very small current to be flow, but ideally this one is 0 ampere. For in forward bias condition, when we connected P type terminal to the positive of the voltage and N type terminal is to be connected to the negative of the voltage, then in P type holes to be the holes is to be the majority carriers, in the N type the electrons to be the majority carriers. So, they repel from this terminal to this terminal and attract in N type. So, most of the holes is to be migrated from P side to N type and electrons are flowing from this side to this side. So, that means electrons is flow from N types to the P type, then a current to be flow, that means the direction of current is direction of the holes flow. So, the holes from P side to the N side, that means the current direction is from P to N. In the reverse bias condition, you see that when P is connected to the negative and N is to be connected to the positive. So, P is the holes. So, holes to be confined here because holes in the holes the charge is positive, then holes is to be confined in that particular area because they attract from negative of the potential of the external voltage. So, the depletion width is to be wide, then no current flow in that particular circuit ideally. This is the very important which has to be asked in the AKTU examination. So, what is the diode current? Basis of the behavior of the PN junction diode. If we plot the diode current in forward bias and the reverse bias, if we take in a what is the relation between them. So, this is the diode equation, ID is equal to ID IS e raised power Vd upon neta Vt minus 1. What is the meaning of ID? ID is the diode current, IS is the reverse saturation current, Vd is the voltage across diode, eta is the constant. For germanium is equal to 1 and silicon is equal to 2, Vt is the thermal voltage and we calculated by Kt upon Q. Ideally at the room temperature, the value of Vt is 26 millivolt. And we draw a characteristics of ideal diode or practical diode. We see that you have to see that this is a germanium diode because the germanium diode having a cut-in voltage is 0.3 volt and the silicon diode is 0.7 volt. So, you see that when we apply a voltage, external voltage and that across the diode, the voltage if we vary is that you see that at 0.3 the current should be increases gradually. So, in the forward bias when P terminal is to be connected at the positive terminal of the voltage and the N is to be connected to the external negative of the supply, then that means a huge current is flow after the cut-in voltage. That means the cut-in voltage where the current is to be started gradually increases gradually. So, this voltage is called the cut-in voltage or knee voltage. If we increase the temperature, that means this graph is at 23 degrees centigrade. If we increase the temperature, or we can say if we increase the temperature 10 degrees centigrade, we have to be increase that. That means this one is 33 degrees centigrade. That means the cut-in voltage is to be dV by this one is dV by dt changes voltage to be changes 2.5 millivolt per degree centigrade. That means if we change the temperature 1 degree centigrade, that means the cut-in voltage to be shifted back at 2.5 millivolt. That means if we increase the 10 degree centigrade, that means the total 25 millivolt voltage, cut-in voltage to be meet here. That means we have to be meet cut-in voltage before the 0.3. So that means the new cut-in voltage is at cut-in voltage at room temperature 23 degree centigrade for germanium case, which one is 0.3 volt. But if we calculate the cut-in voltage at 33 degree centigrade, then the cut-in voltage is to be 0.3 minus 25 millivolt. So we easily calculate the what is the temperature effect upon the VI characteristics. For silicon diode, this is the cut-in voltage is 0.69 or approximately we have to say that 0.7 volt. In the gallium arsenide, for direct band gap material or LED, this one is 1.2 volt, and this is germanium diode, this one is 0.3. What is the cut-in voltage? That voltage we have to be required that diodes to be work. That is the minimum voltage we have to be required that the diodes to be work here. So in that particular circuits, so we can say that particular voltage is called the cut-in voltage. For germanium diode, we required a greater than 0.3 volt for conducting in any circuits. So we draw a VI characteristics of germanium as well as silicon and gallium arsenide. So we see that the cut-in voltage for gallium arsenide is 1.2 volt, for silicon is 0.7 volt, this is the cut-in voltage, and this one is 0.3 volt for germanium. In the reverse bias condition, we have to see that in the reverse bias, in the forward bias, the current rating is milliampere, but in the reverse bias condition, the reverse saturation current in the range of microampere and picoampere. So this is the gallium arsenide breakdown voltage, and this is the silicon, and this is the germanium. In germanium, the range of reverse saturation current in the range of microampere, and in the range of silicon, this one is nanoampere, and for gallium arsenide case, the reverse saturation current in the range of picoampere. As it reduces the required forward voltage and the forward bias current. So we already show that if we increase the temperature, the cut-in voltage to be meet before the actual cut-in voltage at room temperature. When we increase the amount of, so reverse saturation current also we increases when we apply a, when we change the temperature, when we increase the temperature. So in this case, germanium diodes are more sensitive with temperature variation than silicon. So if we design a sensor by using the diodes, so we use the germanium diode because they are more sensitive than the silicon. So germanium diodes are more sensitive, and if we design a any voltage circuit or any control voltage circuit, we have to be designed which are not affected with the temperature. So we use the silicon diode because silicon diode are less dependent upon the temperature variation. So I already show what is the temperature we have to be shifted here, minus 2.5 millivolt per degree centigrade. So easily we have to be calculated. So what is the diode equivalent circuit? So 3 diode equivalent circuit I have to be modeled here. First one is spice-wise linear wire model, and the simplified model, or which one is ideal approximation model. So this one is, this is the diode picture, and this one is N type and this one is P type. So that means this is P terminal, this is N terminal. What is the equivalent voltage? So if we say okay, this is a silicon diode, so we replace the cut-in voltage into the this configuration plus minus, and the voltage of that particular cut-in voltage is 0.7 volt in with respect to the silicon diode. If we take a germanium diode, so the value of this one is 0.3 volt. For germanium is 0.3 volt. If we take in a silicon diode, so the value of this is 0.7 volt. And the what is the average, R average, that means the what is the resistance of that particular diode, which are very less in the range of 1 to 10 ohm. Ideally, we have to be taken 0 ohm, or we can say this one is practical value is 1 to 10 ohm. And this is ideal diode where and we plot the what is the VI characteristic of that particular diode. So we easily, this is the practical characteristics in forward bias condition, and this is the piecewise linear model. And the approximation model, if we because this resistance is very low with respect to the load, ideally we can say the load resistance in the range of kilo ohm and the diode resistance in the range of 1 to 10 ohm. So if we compare this load to this diode resistance, so we ignore this diode resistance with respect to the load. So we ignore it, this resistance here. This is a practical consideration. So this is the plus minus, this is the cut-in voltage for silicon, and this is ideal diode. If we draw this characteristics, so we can say the resistance, that means the diode resistance is 0 ohm. That means what is the meaning of this? Tan theta is infinity, because RD is equal to what is the change in voltage and change in current. But this is y axis and this is x axis, that means y axis I is here. So we can say this is conductance. What is the conductance? Conductance is the reciprocal of GD is equal to 1 by RD, or we can say delta I upon delta V. So we can say this one is ideally 90 degree, or we can say tan theta is equal to infinity. So theta is equal to 90 degree. So that means at 90 degree, this one is here, or we can say no slope is here because the resistance is to be absent. So that means no slope is to be here. So ideally we have to be see that this one is 90 degree. So this is the cut-in voltage, this is the voltage where your diode is to be working here, but no slope is here. So that this this line is to be straight line. But in the ideal case where the cut-in voltage and resistance of diode should be 0 ohm and the cut-in voltage also 0, so they to be shifted here, and the cut-in voltage is 0. That means that your diode is to be started at 0 volt, and they given a infinite current in forward bias. But in the reverse bias condition, no current flow. So this condition is show that in reverse bias current, the saturation current should be 0. So they work as a short circuit in forward bias and open circuit in reverse bias. So this is the ideal approximation of PN junction diode. So we use, this is the piecewise linear model, this is the simplified model, and this is the ideal device. So this is very, very important question regarding the AKTU examination. So next is diode configuration. So what is the meaning of diode configuration? So we some questions I have to be taken. This is a silicon diode. We have to be placed with the battery of having a EMF is E and the resistance R. Then we find the what is the voltage across resistance R. So we easily calculate it. So approximation model we have to be calculated. So we replace this silicon diode because this is silicon diode. So we replace it because this is a P terminal, this is N terminal. So P terminal is to be connected here plus minus, and the cut-in voltage is 0.7 volt, and the E external field is to be applied and this is the resistance R, then the across the what is the voltage we have to be applied, or what is the voltage across the resistance R we have to be calculated by using this approximation model. Then we apply a KVL. So E minus 0.7. So what are the external voltage? Minus to plus, this is plus E, plus 2 minus, this is 0.7. And what are the current? If we say कि this is the I current is to be flow, that this is I into R. So what is the current flow in that particular circuit? Which one is E minus 0.7 upon R? And we want a, what are the voltage across the R? That means voltage across R, which one is equal to I into R. So that means E minus 0.7 upon R into R. That means E minus 0.7. So if we applied a E is equal to 5 volt, that means the VR is 5 minus 0.7. This one is 4.34.